We're here with Maxim Kochurov, who has a background in economics. And for me, I think of you as a mathy person. So I guess I'm curious how you think of yourself in those languages.
Well, I don't think I'm a super mathy person. I better call myself applied statistician.
Mm-hmm.
And I go into math as long as it solves my problems. And you may think that I know a lot about math, but actually I usually go to Stack Overflow or some other resources or very old papers, as long as they serve my specific need at a specific point in time. And if I find them useless, I just throw them away.
Yeah, and it's true. I mean, you haven't studied economics. You have studied economics, not math or anything. So it's quite impressive that you're able to just like pick that up from the University of Stack Overflow.
Yes. Well, in economics, we had quite strong math background.
Mm-hmm.
So we did linear algebra, we did differential equations, a very basic course. There was a little bit of programming, but I got it myself. So I think that was a decent background to be able to read papers that are a little bit unfamiliar territory.
Yeah. And what I also think is really interesting about your trajectory is that you have really gone in depth on two very popular topics. One is deep learning and one is Bayesian modeling. And I guess now you consider yourself a Bayesian, I would assume. And also actually the bridge between the two, Bayesian deep learning. So I'm curious, I guess, how that came to be and what you found studying those topics and why now you're mostly doing Bayesian modeling.
Yeah, indeed. I started with a Bayesian deep learning in a Bayes group by Dmitry Vetrov. It's a Moscow professor that does really good job in the field of Bayesian deep learning and has a lot of publications. So I joined his group, and I was very excited about me, firstly interested in Bayesian methods. Well, I got passionate about, I studied economics, and I felt that Bayesian methodology will help economists to get their job done. And then there was a deep learning boom. I joined the group. And
which year was that?
It was 2015 or 16, somewhere.
That was that first Bayesian deep learning hype. Yeah.
And during this hype, I learned about variational inference, and I got very excited about variational inference and even contributed a lot of it to PyMC, like OPVI that you can find in variational inference model in PyMC. It is mostly inspired by my work in that group. So that was fascinating. Later on, we were doing Bayesian deep learning, and the more I learned about Bayesian methods, the more I got disappointed in deep learning and Bayesian deep learning. Because the way Bayesian statisticians think is in terms of priors, in terms of their prior predictive. What does it mean having this specific prior with this specific mean or standard deviation? So these nuances completely do not translate to Bayesian deep learning. And in neural networks, these priors are just senseless. So there is no way to treat them one way or another, even if they have some maybe structural meaning, like sparsity-inducing priors. In the very end, you can't tell completely nothing about what do they exactly mean, but for maybe some structure. However, in applied statistical models, you can tell everything about your prior, about your model, and that is completely different from this black box field.
Yeah. And then I guess you started with Bayesian deep learning, became a little bit disillusioned with the deep learning field, and then became Bayesian. What was that, like, why do you consider yourself, or what do you find especially powerful about Bayesian modeling?
I think that the ability to reason very nuanced about your model and about your priors, and also translate what others tell you about the problem into priors, into mathematical model, is the most powerful thing in the whole methodology. So this ability is just priceless.
Yeah. And of course, you can really only employ that ability if you're not in a deep learning framework, right?
Exactly.
Because there the model is just
Exactly.
like insane. No one knows what the structure means. But the models that we almost exclusively build at labs, and which you find on the PyMC documentation homepage, is all these like very targeted models where we have very concrete ideas of how this causal graph like fits together, and then place priors and reason on this.
Yes.
Yeah. And how did you become involved then with the PyMC project? So you've been with us a very long time.
So when I was learning the Bayesian path and variational inference, I got into the paper that is about, I don't even remember the exact name, but it was about OPVI. And there was like no sensible implementation. And they found that in PyMC there is some small function called OPVI, and I thought, oh, maybe I can improve that. And then I went to a Theano documentation and downloaded the PDF of the documentation and read that in whole.
Wow, impressive. I don't think anyone has read that in whole.
And then got to PyMC repository, fixing some, firstly some small things, and then went to this function called Taku. He helped me to nail this down into a good implementation, and then I contributed. Then I completely rewritten the OPVI a couple of times, and that's where you find it.
Yeah. Yeah, that was like a killer first pull request to make for sure. I was like, who's this guy? We need to get him on board. Yeah. So all these things, I guess, and today, I mean, you are like one of the most theoretical people on the PyMC Labs team. And I guess I'm curious if you have any tricks that like you know about, or how you think about models that maybe more people should know about, that might be helpful. And it doesn't need to be beginner. It can also be something more for advanced practitioners.
When I start doing modeling, I start with the prior predictive. And this prior predictive tells me how does my data look like, and if my data looks like something sensible, this is a good starting point. And then you can look into this prior predictive, and then you see this like some mean and variance, like this blob of uncertainty. And the next thing I ask myself is, where does this variance come from? Is this the error term? Is it the model? Is it some categorical predictors? Where does it come from? And then try to decompose this variance, that uncertainty blob, into parts. So this I assign to the model. This is to the error term. So it doesn't mean how complex my model becomes. If I keep this uncertainty constrained to what I see on the prior predictive plot, I can be sure that I don't have any extra variance that comes out of nowhere that breaks my assumptions about my data in terms of prior.
Yeah. And I guess this sounds closely related to something else, which I hear you talk a lot about, which is the R2-D2 prior.
Yes.
Can you quickly summarize what that is and why people might want to take a look into that?
So R2-D2 prior, and more precisely, it is called R2-D2-M2-CP prior.
It's a mouthful.
The most nerd name.
Yeah.
Is one of the latest practical contributions to the Bayesian methodology. The first step is R2. R2 is your model goodness. It's,
the classic R squared.
The classic R squared, yes. The D2 part is how you distribute the model variance, that is R squared part of the total variance, to the model parts. So it is the Dirichlet distribution, and each of the components is either a regressor or any other component in the generalized additive model, whatever it is. And M2 is an extension to having this hierarchical, and CP is the assumption that this regressor or component has positive sign or negative sign. So you can not only think in terms of, I think this explains the most variance, but also which direction does it move my explanatory variable.
Okay, so if I understood that correctly, it's a way of specifying how I think my variance is going to be distributed. Yes. And because it's a Dirichlet, it's more specified not in terms of like absolute values, but more relative contributions of variance and how those split together.
Yes.
And on top of that, I have really cool features like, oh, I predict that the benefit, well, that the influence of this covariate is going to be positive, that this is going to be negative. Yeah.
Yes. And this variance explained can be also treated as relative importance to other features. So the more variance you think this particular covariate explains, the more it is important. And you can ask your client what variables you think are more or less important, and he says, oh, this is important, this is less important, like something just in human language. And then okay, this is 1, this is 2, this is 5, like relative contributions of these explanatory variables. That is exactly what your client translates to.
And it makes so much more sense, right? Than like asking like, oh, what is the standard deviation of this? Like, what? What does that even mean? Yeah. That just makes a lot of sense. And actually, I've seen you ask clients these questions where like, and there's all kinds of different ways of asking that. Like, relatively, like, is this more important than that? On a scale of like 1 to 5, how important is it? And what's the sign? So it just makes it very intuitive to communicate. So it seems very powerful. That's a great tip. And now if you think ahead in terms of like where PyMC is today, and is there anything which you think maybe is most promising in terms of the direction for the project, or something which you're explicitly excited about in terms of technological innovation, or just anything else?
The most thing I'm excited about is the technological perspective of PyMC and PyTensor. So the whole transition to alternative backends was so powerful and driving to make sampling faster, robust, and flexible, that you can run your models on GPU seamlessly. And this innovation, I think it was the most important part of transitions from PyMC 3 to PyMC 4 and then 5. And the next generations of PyMC will definitely benefit from having a robust set of backends, because, well, in principle, PyMC is an entry point to any computational backend you can find in the world, maybe, but the PyTorch.
But currently JAX, Number.
Yes. So JAX and PyTorch, they transition to MLIR backend, and that is their final entry point to a LLVM compiler that takes these internal representations and gets you a compiled function. So maybe MLIR is that backend that all the libraries converge to, and that is one of the most promising things to support.
I completely agree. And I think, there was this period, right, where Theano was discontinued, and we were like, oh, well, what's the next best framework for us to build PyMC on? And we, of course, looked into TensorFlow and ultimately decided to fork Theano, which was the right decision. And what that allows us to do is, rather than play catch up with like, oh, well, I guess TensorFlow isn't the latest framework, now it's JAX. Oh, well, maybe it's not JAX, but actually MLIR is where the field is moving, right? And maybe next year it'll be something else. And but we can always like stay ahead on that and just like write targets, transpilers for whatever the most promising backend is right now.
Yes.
And everything else stays the same. So thank you so much for all the work you do in PyMC, for giving us ADVI and a lot of other really cool things. And yeah, and for chatting with us and sharing your knowledge.
Yeah, sure. That's exciting.
Thank you.